Our discussion in this video is the quotient rule for derivatives. See here we're asked to find the derivatives of each of these functions. And we've had experience with functions like this. We can take the strategy of rewriting this function so that it is a coefficient times the power of x. We recognize that we could write this as 3/2 times 1 over x to the fourth. And of course 1 over x to the fourth can be written as x to the negative 4, so this is really 3/2 times x to the power negative 4, and then we can simply use the power rule for derivatives. Finding the derivative now, we would calculate and say that the derivative, or that is f prime of x, is negative 4 times 3/2, which would be what? Negative 12/2. X to a power 1 less than negative 4, well, negative 4 minus 1 is negative 5, of course. And then we see we can simplify this. Negative 12/2, of course, is negative 6. X to the negative fifth could be written as 1 over x to the positive fifth power. And so we would have our final result in this case, negative 6 over x to the fifth power. Now, in our next example, let's see here, we could, I believe we could rewrite this function before we try to find the derivative. We could write this as f of x is equal to 2x cubed divided by x minus 5 divided by x. Now, in this first case, in this first term, 2x cubed divided by x, of course, is just 2x squared. And we could write our second term as minus 5 times x to the power negative 1. And then we would simply be using the power rules for derivatives here. We say, okay, the derivative of this difference is the difference of derivatives. First we take the derivative of the first term. We get 2 times 2, or 4, x to a power of 1. In this case, when we take the derivative, we'll say the exponent negative 1 times the coefficient negative 5. It becomes a positive 5. X to a new power, well, negative 1 subtract 1 is negative 2. And we have to be a little bit careful as we rewrite our answer, that understand that this exponent of negative 2 only affects the x. That is, what we really have here is 4x plus 5 times 1 over x squared. And of course that ends up just being 5x squared, 5 over x squared, pardon me. So we have f prime of x is equal to 4x plus 5 over x squared. Now in this case we've seen examples like this, and this is really a reminder. We could actually create two terms that have a common denominator, and in fact then add these two terms together. So we could rewrite, of course, 4x as 4x cubed over x squared. Let's say 4x cubed, okay, over x squared. I've just multiplied the numerator by x squared and the denominator of 1 by x squared, and then of course plus 5 over x squared. And so we see that our final result would be a denominator of x squared, and our numerator would be 4x cubed plus 5. So far we've done nothing different whatsoever. And it's just a reminder that we've been able to find the derivatives of fractions, at least fractions of these type. Now if you look at the next function though, f of x is equal to x over 2x cubed minus 5. It's just the reciprocal of the function we have here. Well, in this case we could write this fraction as the sum, or difference in this case, of two different fractions. But we can't break a denominator apart with a subtraction. When we add or subtract fractions, we do not add or subtract their denominators, and so there's no way to simplify this fraction in a form that is more than one fraction. And we don't have a means of writing this fraction as a coefficient times x to a power either. So this problem, this function creates a problem that we haven't been dealing with, we haven't dealt with before this time. To take the derivative here requires what's called the quotient rule, and that's what we're getting ready to discuss, of course. This requires the quotient rule. Well, my pen seems to be almost out of ink. I'm sorry for that being so sloppy. Okay, well, let's look and see what the quotient rule actually says. It says to find the derivative of a quotient or of a fraction, we can what we do is take the denominator of the fraction, multiply it with the derivative of the numerator, subtract the numerator multiplied with the derivative of the denominator, and then divide all of that by the old denominator squared. Now, as we saw with the product rule, many times we write that in a simpler form. We refer to u and v without the functional notation of x. So here it's written just the same as above, except it doesn't have the of x in each case. Of course, many of the times we're going to deal with the quotient rule from the point of view of we have a function f that is a quotient, is a fraction. To find the derivative of that function, we take the numerator, once again, times the derivative of our denominator, we take the denominator times the derivative of our numerator, and subtract from that our numerator times the derivative of our denominator, and then we divide all that by our denominator squared. Now, as we look at this, it's important to realize something that is not said here. It does not tell us that to find the derivative of a quotient, we simply take the derivative of the numerator and divide by the derivative of the denominator. In fact, that will not work. And we can even verify that with the examples that we just saw a moment ago. If we recall from one of our problems just a moment ago, we had the function f of x equal 3 over 2x to the fourth. We wrote that as a power of x and found the derivative to be negative 6 over x to the fifth power. Now, if we were to use the quotient rule on this, we would name our numerator u, so u is equal to 3, our denominator v, 2x to the fourth, and in the rule we need to know not only v and u, but u prime and v prime. That is, the derivative, u prime is the derivative of the numerator. Well, u is 3, so the derivative of a constant 0. And we need to know the derivative of our denominator. Well, our denominator, v, is 2x to the fourth, and the derivative of 2x to the fourth, of course, is 8x to the third power. And so we would place these into the quotient rule formula, and we'd say the derivative of our function is our v value, which is the denominator, times the derivative of our u value, that is the derivative of the numerator, that's u prime. So we can read over here. And then we subtract u, which is our numerator, which is just 3, and we multiply that with v prime, which is the derivative of our denominator. Well, of course, our denominator was 2x to the fourth, and that derivative then was 8x cubed. And then we divide all of that by 2x to the fourth being squared. And you can see here when we simplify this, we get a negative, here 2x to the fourth times 0 is of course 0. Here we have minus 24x cubed when we multiply these together. When we square this denominator, we get 4x to the 8th. And of course that simplifies to negative 24x cubed over 4x to the 8th. But 24 over 4 is 6. X to the third over x to the 8th is 1 over x to the 5th. And so we get the same result using the quotient rule. Now, it's very important, though, to recognize that what we did not do is say that the derivative was simply the derivative of the numerator, that would give us 0, divided by the derivative of the denominator, which would be 8x to the third. But of course 0 divided by anything is 0, and our derivative we know is not 0. We do not find the derivative by simply taking the derivative of the numerator and dividing by the derivative of the denominator. Let's get back to the problem that started this discussion. We have a function f of x that is x divided by 2x cubed minus 5. And we decided earlier that there wasn't a way for us to write this function in a way that allowed us to use old techniques for finding derivatives. And so we're forced to use this quotient rule. Now, we might start out once again by remembering that we were naming, in of course the way we've written this, the numerator u and the denominator v. And to use the quotient rule, we not only need the u and the v, but we need the derivative of u and v. So we'll start out by naming u as x. And then just as quickly we'll name v, the denominator, 2x cubed minus 5. Now, as I mentioned, we're going to need the derivatives of each of these, and so u prime, the derivative of x, is simply 1. And v prime, which is the derivative of the denominator, is simply 6x squared. Now we can use this information to put into the quotient rule formula. So we're looking for f prime of x. Okay, now what we're going to do, remember, is we're going to write down, we're going to fill in, of course, our v here times our u prime here minus our u times our v prime, and so on. But as I do this, we've got this to go by, but I'd like you to really remember that what we have is denominator times derivative of numerator minus numerator times derivative of denominator, all divided by denominator squared. And we can review and look up here and make these decisions. We really don't need this tool. So let's get prepared here. It's going to be a fraction, so I'm going to go ahead and put down my division bar. And let's begin. It says take v, which is the denominator. Well, the denominator being 2x cubed, I'll write down 2x cubed, that is minus 5. There's denominator times derivative of numerator. Well, we look up here, here's the numerator, its derivative is 1. And then minus, well, I see that I didn't make my division bar long enough. Minus, we turn the tables. Now it's the numerator, which is just x, times the derivative of the denominator. Now we can look here for v prime, or we could simply look here. Here's our denominator. Its derivative is 6x squared. And so we would put our 6x squared here. And then we divide this result, this numerator, by the old denominator squared. So we take our 2x cubed minus 5, and we square that. Now, as I've shown in the past, I've put the resulting derivatives where I had a derivative that I filled in. I just wrote that derivative in brackets. That it will help me later on check my work, realizing where I've actually calculated a derivative, an intermediate derivative. So, I believe in this fraction we can do a little simplification in the numerator, and we'll see about doing that. We see that we have 1 times 2x cubed minus 5, so that'll just be 2x cubed minus 5, and we have minus x times 6x squared, which will be negative 6x cubed. So let's build our fraction. Well, here, as I said, we have 2x cubed minus 5, which comes from this multiplication, and then we have minus 6x cubed. And our denominator, of course, is 2x cubed minus 5 to the power 2. Now this numerator will simplify further. We see that we have like terms. 2x cubed and minus 6x cubed. So that will result in a negative 4x cubed. And we still have minus 5. And that's all divided by 2x cubed minus 5, the quantity squared. Now, we would normally look and see whether or not we can factor and reduce this fraction. But if we compare what we have here and what we have here, we see that we really have no factoring possibilities, except that we could factor out a negative 1. So an alternative way to write this is imagine factoring out a negative 1 from that numerator. That would give us a negative 1 times 4x cubed plus 5. But let's put that factor of negative 1, rather than in front of the numerator, in front of the fraction. And then we're divided by, of course, 2x cubed minus 5 to the power 2. This would be an alternate way to write this result. Either one, I think, would be acceptable. What we'll find that we do a lot in this section is after we do our calculations, we check in the back of the book and see if we need to change the form of our answer. Well, let's try another example. Example 2 will be a little bit more involved, but if we keep organized, we shouldn't have any trouble. Here's example 2 of our quotient rule for derivatives. Our function is f of x equal x cubed plus 2x minus 1 divided by x squared minus 1. And we're, of course, to find the derivative f prime of x. Well, it's important, of course, that we identify the numerator u and the denominator v, and that we also identify u prime and v prime, which will be needed. So, as you see, I've identified u, the numerator, x cubed plus 2x minus 1, and of course the derivative of that numerator is 3x squared plus 2, as I look above. Also, I've identified the denominator as v, as we see here, which is, of course, x squared minus 1, and the derivative of that denominator, v prime, is just 2x. Now, I suggest that as you practice the use of this quotient rule, you practice writing down the rule as you see it here and saying it to yourself, and before long you know that you'll have it memorized. So that is, the derivative of f is the denominator times derivative of numerator minus numerator times derivative of denominator, all divided by denominator squared. And of course, I've color-coded these so that we can see as we fill them in. Now, if we remember it that way, sometimes we can just refer to the original function. That is, we have denominator, x squared minus 1, times derivative of numerator. Well, derivative of x cubed plus 2x minus 1 is 3x squared plus 2. Of course, we can also get it directly from our labelings that we've already done. Here is v, and here is u prime. Remember, v times u prime. And then it's minus u times v prime. That is, minus the numerator times derivative of denominator. Of course, the numerator is x cubed plus 2x minus 1. That's our u. Times the derivative of our denominator, v prime. Well, we can look up here and say there's our denominator. Its derivative is 2x. Or we could have used it from here as we prepared the job. And then that's all divided by the original denominator squared, v squared. So we take x squared minus 1 and we square it. That's v squared. Then we see that we have some simplification in the numerator that we can do, that we use polynomial multiplication to actually multiply this x squared minus 1 and the 3x squared plus 2. And of course, x squared times 3x squared is where we get 3x to the 4th. And x squared times 2 is where we get 2x squared. Negative 1 times 3x squared is negative 3x squared. And negative 1 times positive 2, of course, is negative 2. Now, over here on the side, we need to be a little bit more careful as we do this work. And I want you to recognize that I'm looking at this. This minus sign is what I'm worried about. And so I'm thinking of this as actually a negative 2x times the x cubed plus 2x minus 1 that I have in parentheses. So what I'm thinking here is I do this multiplication so that I get the signs correct. And of course negative 2x times x cubed is where I get negative 2x to the fourth. And negative 2x times a positive 2x is where I get negative 4x squared. And finally negative 2x times a negative 1 is a plus 2x. And so that's the result that I get from this part of the numerator. All divided by x squared minus 1, the quantity squared. And then we see in the numerator we can still combine some terms. We see that we have 3x to the fourth and a minus 2x to the fourth, which is 1x to the fourth. And we've got 2x squared minus 3x squared and a minus 4x squared. And as we combine those, we'll get minus 5x squared. And then that leaves us with just plus 2x and minus 2. For our numerator, we now have our numerator, all terms combined. Many times we would see if we could reduce this fraction, but in this case we're in reduced form, and so there we have the result for our derivative. Here in example 3 we have a function, a rational function, or a function that's a fraction actually. 3x squared plus 2 times the square root of x divided by x, and we're to find the derivative. So our first inclination is to use the quotient rule since we do have a fraction, so we could label our numerator as u. So we have u is equal to 3x squared plus 2 times the square root of x. And our v, which of course is x. And we know to use the quotient rule we need to know the derivative of the numerator and the derivative of the denominator. Of course the derivative of the denominator is easy for us to calculate. V prime, the derivative of x, is simply 1. But we have a little difficulty with calculating the derivative of 3x squared plus 2 times the square root of x in this form. We recognize that if we rewrite u as 3x squared plus 2 times x to the 1/2 power rather than the square root of x, then we'll be better prepared. So now when we look at the derivative of this expression, of course 2 times 3 is 6, x to the first power. When we take the derivative of the first term, when we take the derivative of the second term, we're going to have the exponent 1/2 times the coefficient 2. 1/2 times 2 of course is 1. X to a power that is 1 less than 1/2. Well, of course 1/2 minus 1 is negative 1/2. So now we're ready for our derivative. G prime of x is equal to, let's see what we've got. It's going to be a fraction. Where the numerator is going to be denominator, that's v, times derivative of numerator. Now that's one we didn't do in our head. We had to almost go through this process. So derivative of the numerator, u prime, is 6x plus x to the power negative 1/2. And then it's minus the numerator, which is u, the numerator, 3x squared plus 2 times the square root of x. It appears that we need to lengthen this division bar. So our numerator, 3x squared plus 2 times the square root of x times the derivative of our denominator. Well, our denominator is x, its derivative is 1, or our denominator is v, and v prime is 1, so times 1. As I mentioned to you earlier, and I failed to do it this time, that I normally put these intermediate derivatives in brackets. So normally I would have put brackets here. And then of course all that's divided by the old denominator, x, being squared. That's v squared. And so there's the result of our derivative. But of course there's always algebra involved after these derivatives, so we need to see if we can't clean things up, that is, expand our numerator and see what simplification might occur. Okay, so as we multiply this x to this binomial, we'll have x times 6x, which of course is 6x squared. And we'll have x times x to the negative 1/2 power. Well, that's x to the first times x to the negative 1/2 power. So we add the exponents 1 and negative 1/2, and we get a positive 1/2 power. So we have x to the positive 1/2 power here. And in this case, we just have a factor of 1, and so this negative sign is going to distribute through here, and we're going to have minus 3x squared, and we're going to have a minus 2 times the square root of x. And of course all that's divided by x squared. And then we look and notice that we really can write this as the square root of x. This is really the square root of x. And so as we simplify further, we see that our numerator we're going to have a 6x squared minus 3x squared, which of course is just 3x squared. And we're going to have a positive 1 square root of x and a minus 2 square root of x, which is minus 1 square root of x, or just minus square root of x. And all of that is divided by x squared, and that would be the result that we would have. That looks like certainly a derivative that we've calculated. Now, it may have occurred to you as we worked on this problem that this is not the only way to do the problem. In fact, in this case, we could avoid using the quotient rule at all if we recognize that we could break this fraction down into a couple of fractions, and we could begin to simplify. So, in other words, we could have written this g of x as, before we got started, as 3x squared divided by x plus 2 times the square root of x divided by x. Now that can be further simplified by simplifying the fraction 3x squared over x, of course, which is just 3x. Now in this case, we really have x to the power 1/2 here. And we have x to the power 1 in this case. So we would actually get 2 times x to the power, let's see, 1/2 subtract 1. The exponent 1/2 on this x, subtract the 1 here, is negative 1/2. So we could have looked at the problem in this fashion, and then we would be ready to take the derivative of this form of g. So g prime of x would be equal to, well, let's see, the derivative of 3x would just simply be 3, and the derivative of 2x to the negative 1/2, well, negative 1/2 times 2 is a negative 1, and when we decrease the exponent negative 1/2 by a 1, negative 1/2, oh goodness, let's see. Let's look over here. Negative 1/2, that's the old exponent, subtract 1. Well, that's negative 1/2 minus 2 over 2, which results in negative 3/2. So our exponent here is negative 3/2. And of course that could be written, g prime of x could be written as 3 minus x to the power negative 3/2. And we would say, oh my goodness, these answers are nothing alike at all. Well, of course, we would never leave a negative exponent. And so we could write g prime of x actually as 3 minus 1 over x to the power positive 3/2. Now, let's consider this x to the positive 3/2 a little further. Let's think about that. X to the positive 3/2, remember, means the square root of x cubed. But of course the square root of x cubed, since x cubed can be thought of as x squared times x, the square root of x cubed is x times the square root of x. So g prime of x is really 3 minus 1 over x times the square root of x. Now again, these two answers look significantly different. Maybe we need to investigate further and see what we could do about this. Well, for one thing, we could rationalize this denominator. So we'll multiply the numerator and denominator by the square root of x. Okay, then we would have g prime. G prime of x would be this 3 minus, let's see, we have square root of x in the numerator, and here we have x times the square root of x times the square root of x. Well, these two square roots of x together give us another x, so we have a denominator of x squared. Now we see where this denominator of x squared is beginning to come from. So we would finally multiply this 3. We need a common denominator. So we'd multiply 3 by an x squared in the numerator and an x squared in the denominator. And so we would rewrite 3 as 3x squared over x squared. And of course we have minus the square root of x over x squared in this position. And ultimately then we can see that we can combine that into a single fraction. And we would have g prime of x is equal to 3x squared minus the square root of x divided by x squared. Now, in this particular example, there's a question about which way we would choose to do the problem. We may have stopped way back up here. See, we may have stopped actually at this level if we didn't know any better than to trying to get the same answer that we had here. And of course, if we would have stopped at this level, our process probably was much simpler. We didn't have to use the quotient rule. But you're going to be faced many times with the result you get and trying to make it look like the result that you see in the back of the book as an answer. And so we're going to have to be used to this type of work in algebra. Well, that's it for this example. Well, example 4 requires us to use the quotient rule to find the equation of a tangent line. So as you can see, the problem is find the equation of the tangent line to the curve y equal 1 over x squared plus 4 at the point 1, 1/5. And many times I look at these problems and I make sure that this point's actually on the curve, so I imagine putting a 1 in for x. So I'd had 1 over 1 squared plus 4, and of course that is 1/5. So certainly I'm convinced that this point is in fact on the line. Remember, to find the equation of any line, much less that of a tangent line, there's two pieces of information we need. We need a point on the line, and we have that. That's given to us. This point of tangency, the point we're tangent at, of course is on the curve, and that's the position on the curve that the tangent line touches. So we need a point on the line, and we also need a slope of the line in question. So in this case we need the slope of this tangent line, and that's useful because remember how we find slopes of tangent lines? We use the derivative. So our job will be finding the derivative of y with respect to x, and when we find that derivative, then we will evaluate it at the point, the x value of the point of tangency. So we'll evaluate it at x equal 1. So we will work on finding that derivative. That's really what we're after right now. So as we look at our function y equal 1 over x squared plus 4, we recognize, as we said, that that is in fact a quotient. And so to use the quotient rule, we'll begin by remembering that we have what? It's the derivative is the denominator of the original quotient. Well, the denominator is x squared plus 4, so denominator times derivative of numerator. And so let me just write that in this fashion. Derivative of, and the numerator, of course, is 1. And then we subtract, let's see, we subtract the numerator, which is 1, times the derivative of the denominator. Now, let's just write that. I know that we can do this in our head, but let's write that. The derivative of the denominator. Well, the denominator is x squared plus 4. So we're indicating what we need to do to calculate that derivative. And then, of course, all that's divided by x squared plus 4 squared. That is the old denominator squared. Now we can go back in and we can do some quick calculations, I believe. In this case, we have x squared plus 4 times the derivative of 1. Well, the derivative of any constant is 0. So we end up here with x squared plus 4 times the resulting derivative, which is 0. Now, we'll come back in just a moment and recognize that, of course, x squared plus 4 times 0 just creates a 0. And then we have minus 1 times the derivative of x squared plus 4, and the derivative of x squared plus 4 we recognize as 2x very quickly. And so all of that is divided by x squared plus 4, that binomial being squared. Then we look here and we say, oh, well, okay, we create a 0 in this position. So dy dx is in fact 0 minus 2x, which is just negative 2x. And of course that's divided by x squared plus 4 to the power 2. Now the whole reason we were after that derivative is so that we could calculate the slope of our tangent line. So what we know that we need to do here is we need to take that derivative and we need to evaluate it at x equal 1. Whoops. We need to evaluate it at x equal 1. So as we do that, let's see, x is 1, so we have negative 2 times 1 divided by 1 squared, that's a 1 in for x, plus a 4, and then that binomial, or that result, is squared. So we have the derivative of y with respect to x evaluated at x equal 1 as the number negative 2 over, let's see what we have here, 1 plus 4, 5, we have 5 squared. And so that tells us the important piece of information that we were really after. That tells us the slope of our line is negative 2 divided by 25. Well, now we use this information to actually come up with the equation of the line. Remember, we do that by employing the point-slope form of the equation of a line. That is, y minus y sub 1 is equal to m times x minus x sub 1. And as we recall, the m represents the slope of the line in question, and we have that slope as negative 2 over 25. And the x sub 1 and y sub 1 represent the x value and y value of a point we know is on the line. So x sub 1 is 1 and y sub 1 is 1/5. So we go ahead and we replace these values, y minus our y value, which is 1/5, is equal to our slope number, which is negative 2 over 25, times x minus our x value of the point of 1. So we need a little bit more room here. Now we begin simplifying this. So we have y minus 1/5, minus 1/5 is equal to, on the right side, negative 2/25 times x plus 2 over 25. 2 over 25. Now, then we would add a 1/5 to both sides, of course, so we'd have y is equal to negative 2 over 25 times x plus 2 over 25 that was originally there, plus the 1/5 that we're adding on both sides. And then you can see easily what our result is going to be. The equation of our tangent line is y is equal to negative 2 over 25x plus, let's see, we're going to rewrite this as 5 over 25. So that's really what we're about got ahead of myself. We need to multiply the numerator and denominator by 5, so we have 5 over 25. We have that common denominator. And finally, we have y is equal to negative 2 over 25 times x plus 7 over 25. And that, in fact, is the equation of the tangent line in question. Our example 5 requires that we do a little bit more work than in our other examples or previous examples. So here we go. We find the derivative of the function f of x equal x squared times e to the x, all divided by 1 plus 3x squared. Well, it's apparent to us that we're needing to use the quotient rule. So we apply that quotient rule, and here's the derivative that we get. Well, no, not exactly. Let's make sure that we understand how these pieces came into being. Remember the way the quotient rule works. And it's important for us to begin to start doing these things without writing down the u's and v's, because you can see it gets very complicated very quickly. So what we're really doing is we find the derivative. We say take the denominator of the function and multiply with the derivative of the numerator. So here we have, of course, this is the denominator of the function. So we say take the denominator of the function and multiply with the derivative of the numerator. Well, of course, our numerator is x squared plus e to the x. So we're going to multiply with the derivative of that numerator, x squared e to the x. The problem is we can't do that in our head. That's much more complicated, that we'll recall in a moment. Then we say subtract, we reverse it, the numerator times the derivative of the denominator. In fact, let me make it real clear here that we're not only worrying about this numerator, but it's the derivative of the numerator, and that's the way we write that down, since we can't do it in our head. And then, of course, we have the numerator alone. That's what this says, the numerator minus the numerator times the derivative of the denominator. Well, this is saying the derivative, and that's of the denominator. So that's, of course, the v prime. And then we divide all of that by the original denominator squared. So there's the original denominator, and we square it. So that's how we get this expression down here. And of course, here we see the long division line of that fraction. Now, our real issue is we can find this derivative, of course, in our head. Derivative of 1 plus 3x squared is just 6x. But this derivative is not so easy. And that's the reason we need to be able to learn how to write this. This derivative requires that we use the product rule, because after all we have a variable x squared times a variable expression e to the x. So now we have to remember, oh my goodness, how do we deal with the product rule? Well, let's see. Let's write this down. The derivative with respect to x, the derivative of x squared e to the x. Now remember, the way the product rule works is we say first function times derivative of second. Now in this case we may be able to remember what the derivative of e to the x is. But let's think about it as first function times derivative of second. That's the way we write that. And then we reverse that. Plus the second function times the derivative of the first. Well, the first function is x squared, and so we are taking the derivative of x squared. Now I understand we could do that in our head, but I'm trying to practice this notation, as in this case where we can't find that derivative all at once in our head. So here of course we have x squared, and the derivative of e to the x is simply e to the x. And of course here we have the e to the x, and the derivative of x squared is simply 2x. And so we can go back in and we can kind of make this look a little better by writing it as x squared e to the x plus, we'll write this factor in front of e to the x, we'll write it as 2x e to the x. Now you understand here that this is going to go in the replacement of this spot right here. And so we don't want to factor that because we still have to have it multiplied in this case. So we've got a big string that we have to deal with. So let's begin to rewrite that. Let's put this in this position and see where that puts us. Now we'll kind of go on to the next page actually. In fact, what I would do is I would start writing this over again. Rather than, this is maybe over my support work, and now I know what to put in here, and I want to make my work that someone else reads nice and clean and neat. Okay, now that we've calculated this derivative, we're ready to actually replace it with x squared e to the x plus 2x e to the x. And of course we can calculate this derivative to be 6x. So as we rewrite our derivative, as we said, we've put the resulting derivative using the product rule here. And of course this derivative is easy for us to do. We simply get 6x. Now we see what we have is a binomial times a binomial in this position. So we'll need to do this multiplication. And as we see doing this multiplication, the result we get, well, let's see, a 1 times x squared e to the x is x squared e to the x. A 1 times 2x e to the x is 2x e to the x. A 3x squared times x squared e to the x will give 3x to the 4th e to the x. And finally, 3x squared times 2x e to the x gives what? A 6x cubed e to the x. And then we have our subtraction sign, and of course here we have a multiplication, which is going to create 6x cubed e to the x. And then we notice, of course, that this 6x cubed e to the x minus this 6x cubed e to the x will allow us to do a little simplification. So we look at that simplification where those add to 0. And we look to see if there's any other simplification we can do in this numerator. And we might notice that we can factor out an x because every term has an x in it, and we can factor out an e to the x since every term has an e to the x in it. But for what purpose? Factoring alone is not simplifying. And the reason we would want to factor here is if we could reduce this fraction. And this is not, that factoring will not create a factor that we can reduce. That will not create this factor 1 plus 3x squared. So there's no real purpose in doing our factorization there. We simply would be happy with this as the result. This would be our final answer. We'll be very happy with that. Now, of course, as we mentioned before, this required a lot more work. And the main point of this problem, or the main reason I wanted to do this example, was to understand that it's going to behoove us to not just really worry about writing down u's and v's, but remembering denominator times derivative of numerator, and then being able to write how we say derivative of numerator, because we can't do that calculation in our head. Then in our support work, we would do that work over here on the side that would allow us to make this calculation, which we have here. And then, of course, we need to remember minus numerator times derivative of denominator divided by denominator squared. That's really the point of this problem, is being able to remember the formula using numerator and denominator ideas, and also being able to write each of these expressions derivative of. Well, example 6 illustrates another type of issue that we run into occasionally. We're to find the derivative of y is equal to the fraction 2 over x to the 4th plus 1 plus the fraction 3 over x. Now, in this case, we don't use the quotient rule directly because we don't have a single quotient. We actually have the addition of two fractions. And of course, when we have things that are added together, to find the derivative is the sum of the first expression plus or minus, appropriately, the derivative of the second expression. So that's what I've written here. Derivative of y with respect to x, that's why we write the derivative of y rather than f prime, since we don't have f. And of course the first fraction, so the derivative of the first fraction plus the derivative of the second fraction. Now, to find this derivative of the first fraction will require us to use the quotient rule. So we get ready to say, let's do that work right here. Let's say the derivative of y, excuse me, that's not what we're working on. Let me erase that. Okay, we'll start again. This derivative, the derivative of 2 over x to the 4th plus 1. Of course, that's x to the 4th. Now we're going to practice as we did in a previous example. We're not going to worry about naming u and v. We're going to remember how this works. To find the derivative of a quotient, we say is the numerator, which is x to the 4th plus 1, times the derivative of the denominator. In this case, we can actually calculate, the derivative of the numerator. And we can actually calculate the derivative of the numerator very easily because the derivative of a constant is 0. I'm sticking with this idea that I'm putting my resulting derivatives in brackets here. Then we say subtract the numerator, which is 2, times the derivative of the denominator. Well, we actually might be able to calculate that in our head as well, but it's the derivative of x to the 4th plus 1. And then all of that, of course, is divided by the original denominator, which is x to the 4th plus 1, that squared. Now we look in the numerator and we see that we can, after all, we can write this x to the 4th plus 1 times 0. Well, it doesn't matter. Any expression times 0 would be 0. And so our numerator will simply be this negative 2, or a 0, we'll go ahead and write, minus 2 times the derivative of x to the 4th plus 1. And of course that derivative is simply 4x cubed. All over, that is all over x to the 4th plus 1 being squared. And then we see, of course, that results in just a negative 8 x to the 3rd over the binomial x to the 4th plus 1, the quantity squared. Now, of course, what I would have normally done is do this work on my paper where I could write a little smaller over in the margin area or over to the right, so that I would have it as a reference so I know how I actually did this work. But of course, we understand that this expression is going right here in place of this derivative. Okay, as we rewrite and replace, our result will look like we've completed the first derivative, and of course we've done that on the side. Now we turn our attention to the derivative of 3 over x, and we recognize, of course, very easily that is a quotient, but that's a non-productive way to do this. We can find this derivative much easier that if we consider 3 over x as 3 times x to the power -1. So if we just write 3 over x in this fashion, then we know the derivative is very easy for us to calculate. We'll say -1 times 3, which of course gives us -3, and when we reduce -1 by 1, -1 subtract 1 is -2. And then we remember that can be rewritten as -3 times 1 over x squared, or a much better form, -3 over x squared. So of course this goes in this position. So we do that replacement, and we see that our derivative, of course, is -8x cubed over x to the 4th plus 1, the quantity squared. Oh, and notice that this was a -3x over 3x squared, and so that ends up replacing this plus sign with a minus. This is probably the position that we would stop at, and this would be the result we would expect to leave as our answer. Now, I might point out in this case that occasionally you're going to run into the situation where your answer doesn't match the one in the back of the book. And for instance, in this case, we might have a single fraction answer in the back of the book, which would imply to us that we'd actually need to do the subtraction that we have stated between these two fractions. So we'd have to get a common denominator, which would be the product of these two. So this numerator and denominator would need to be multiplied with x squared, and then this numerator and denominator would need to be multiplied with x to the 4th plus 1, the quantity squared. Which, of course, if we continued on that path, I suppose, let's look at what we might have if we did that. We'd have a -8x cubed multiplied with an x squared divided by our, that's an x squared, I'm sorry about that. It certainly doesn't like me writing that exponent. It's very strange. I apologize for this step where can't even erase it. Well, let's continue and just remember that we have an x squared in this position. There we go. One more time. Let me try to clean that up because it's sure bothersome. Okay, I apologize for this delay. So we have an x squared in this position, and of course we have x to the 4th plus 1, the quantity squared, times x squared. We just multiplied numerator and denominator by x squared. And of course here we're multiplying the numerator by 3x to the 4th plus 1, the quantity squared, divided by the original x squared multiplied with this x to the 4th plus 1, the quantity squared times x squared. You see, in this example, we're not really going to, I mean, we could expand this further. Let me stop here. I don't really like what we're getting accomplished here, so I believe I will just stop, and we'll be happy with what we've got. Example 7 is a quotient that involves trigonometric functions. And as we've discussed before, we a lot of times like to prevent using the quotient rule because it's such a complicated rule. And so it occurs to me that since we have a monomial or a single term denominator, that we could actually break this function into the sum of two fractions. That is, we could write it as sine of x over cosine of x plus cosine x over cosine of x, as I've done here. And of course, sine of x over cosine of x is tangent of x, and cosine x over cosine x, of course, is 1. But this doesn't help us in this problem because we don't know how to find the derivative of the tangent of x, although we know how to find the derivative of 1. So this is a little bit of an issue for us, and doesn't seem like it's really going to help us. So we go back to the use of the quotient rule. Well, when we use the quotient rule, we need to remember the way we set it up, that we first say take the denominator and multiply with the derivative of the numerator. Well, the denominator is cosine of x, and the numerator is sine x plus cosine x. So cosine x times derivative of sine x plus cosine x. And then we subtract the numerator, which we have here, times the derivative of the denominator, which we have here. And then we divide all that by the old denominator being squared. Now, it's important to write it in this format. Now, some of these we may actually have been able to do in our head, but we go ahead and write it this way so we can take our steps nice and easy and not get all excited and make silly mistakes because we're trying to do too much at once. So in this next step, what I've done is I've taken the derivative of this sum. And of course, that means we take the derivative of the sine of x, which is cosine x, and then we take the derivative of cosine x, which is negative sine x, and that's the reason this turned into a minus sign from a plus sign. But it's also important to remember that this result's going to be multiplied with the cosine of x. So it's very important that we show this in some kind of grouping symbol, at least parentheses. But I stick with my routine that when I have a step that has an intermediate derivative in it, that I show the result of that derivative in brackets, and that helps me know where that came from later on. Okay, now we're subtract the sine x plus cosine x times the derivative of cosine x, which is negative sine x. So that's the result we have here. Let's see, our next step down here, pardon me, is to actually do this distribution. So we have the cosine of x times the cosine of x. That's how we get cosine squared x. And then the cosine of x times negative sine x. And so we get negative cosine x sine x. And then subtract. Oh, but look what I've done here. When I have a subtraction sign and I have an expression that's more than one term and multiplied with something else, I need to be very careful that I set it up so I make sure I get the correct sign pattern. So what I've done is I've moved this factor, negative sine x, to the front, and the negative sign I had here is originally here, and then I have this minus sine x, and that makes me recognize that I really have the negative of a negative, which is plus. And so I'm really changing this into a plus before I multiply. So I have a positive sine x times a sine x, sine squared x. And then a positive sine x times a cosine of x, which I could have written sine x cosine x. But I wanted to make sure that I had it in the same order that I had done a multiplication like this before, so that I would recognize that I actually have the same two terms, but one's negative, one's positive. Now, that brings along the fact that we could actually these two add to 0, and so that's going to be leaving us with just the cosine x squared term and the sine squared x term in the numerator. Now, I've gone ahead and taken the next step, but I want you to be careful because we see things like this an awful lot, that we're in the middle of the problem, in the heat of the problem, on a test or on homework, and we get to this step and we're so glad to have recognized so much and get this far, but then many times we just quit because we don't remember or don't recognize old terms or old forms. Remember, from trigonometry, we normally see sine squared x plus cosine squared x is 1. And likewise, cosine x squared plus sine squared x, cosine squared x and sine squared x is 1. And so we replace the numerator with 1, and of course we have the same denominator. And then we recognize that 1 over cosine x is secant x, so 1 over cosine squared x, of course, is secant squared x, and we're finally to our result. This kind of actually leads us into the next example where we can actually do a lot more with other trig functions because we have the quotient rule that we can deal with. So let's look at the quotient rule applied to the tangent of x problem as our next example.